Usually when we talk about a medical diagnosis, there's this expectation of absolute precision. Like it feels like engineering, right? You break your arm, the x-ray shows that jagged white line, and the doctor just points to the screen and says, there it is.
Yeah, it's a very comforting binary.
Right.
Broken or not broken. I mean, we naturally gravitate toward things that can be categorized neatly, where that line between true and false is just, visible to the naked eye.
Exactly. But then you step into the world of human-AI collaboration, especially in these really complex fields, and suddenly that pristine x-ray machine is just shattered.
Oh, completely.
We're looking at a diagnostic landscape that is, well, honestly, it's murky. You have experts profoundly disagreeing, data arriving at totally random times, and the AI is just sitting in the middle of it all.
Right. Tasked with somehow figuring out what the actual ground truth is.
Yeah. Welcome to the Deep Dive. Today we are looking at a stack of internal documentation and pilot data from the HumAIne project. And our mission for you today is unpacking their highly anticipated blueprint for building actual scalable trust in human-AI collaboration.
It's a huge topic.
It really is. If you're listening to this, you likely already know that getting humans and AI to work together seamlessly without, bottlenecking each other is basically the holy grail.
Yeah, absolutely.
But how do you actually architect that?
Yeah.
Well, we've got our hands on HumAIne's validated library of integration patterns. So, okay, let's unpack this. Why is a systematic collection of these integration patterns such a massive breakthrough right now? Because looking at the documents, it honestly seems like people were just winging it before.
Yeah, they kind of were. And the historical context here is really what makes this library so vital.
Okay.
In standard machine learning, so your basic predictive models or like recommendation engines, we have established playbooks.
Right, the reliable stuff.
Exactly. But the HumAIne project operates at the bleeding edge. I mean, we are talking about paradigms like swarm learning.
Where multiple decentralized devices train a model without sharing raw data.
Right, exactly. Or neurosymbolic AI, which tries to combine the pattern recognition of neural networks with strict human-readable logical rules.
Right.
In those niche spaces, there has just been a severe lack of systematic pattern collections. It has essentially been the Wild West for developers.
Wow.
So AI solution integrators have basically been forced to reinvent the wheel every single time they deploy one of these interaction-heavy systems.
Just building from scratch every single time they hit a new problem.
Every single time.
Which means a massive amount of inter-system complexity, and the cross-system integration effort just balloons totally out of control.
Yeah, it becomes unmanageable. So the unique selling proposition of the HumAIne's source material, the USP here, is that it finally provides a dedicated library of generic boilerplate code templates.
Okay.
These templates have been practically applied and they've been validated in their pilots, so they offer a proven shortcut.
So integrators aren't just guessing anymore.
No, not at all. They are applying parameterized patterns that are specifically designed to handle the inevitable messiness of human-AI interaction, which drastically accelerates development.
So we're giving you the blueprints instead of just handing you a pile of bricks and hoping you build a house that doesn't collapse on itself?
That's exactly it.
But before we get into the specific behavioral patterns, like how the system handles human disagreements or, real-time emergencies, we really need to understand the engine running all of this, the architectural canvas.
Yeah, because without a robust foundational orchestrator, these interaction patterns simply have nowhere to live.
Makes sense.
The system detailed in the sources is designed around orchestrating AI pipelines using a highly organized machine learning operations, or MLOps, approach.
MLOps.
And the absolute core of this toolkit is Kubeflow.
Okay, just to ground that for a second for you listening, Kubeflow is doing the heavy lifting for the entire machine learning lifecycle, right?
Yeah.
Development, deployment, monitoring. But why Kubeflow specifically? I mean, there are other platforms out there.
Well, when dealing with sensitive fields like medical diagnostics or proprietary manufacturing, you need absolute watertight isolation between projects.
Right.
Kubeflow provides simultaneous management of multiple projects while achieving multi-tenancy.
Okay.
It maintains strict boundaries through Kubernetes namespaces and role-based access control, or RBAC.
Which makes perfect sense. If you have different teams or even different hospitals working on the same overarching infrastructure, you absolutely cannot have them accidentally stepping on each other's toes.
No.
Or, accessing patient data they shouldn't see.
Exactly. RBAC ensures that security isn't just an afterthought, it's baked directly into the foundation.
Right.
On top of that secure layer, the architecture utilizes what the documentation calls a two-layered orchestration architecture.
Okay.
This is how the system actually manages the flow of work and data.
Let me try to map this out for you, because when I was looking through the HumAIne pilots, this dual structure really stood out. Picture your own screen right now. The first level uses an Elira-based visual plugin.
Right.
Think of this like laying down the train tracks. It's a drag-and-drop interface where you construct the sequential, step-by-step machine learning workflows.
Yeah, things like fetching the data set, pre-processing it.
Training the model from Jupyter notebooks or Python scripts.
Exactly.
It's very structural and linear. Meanwhile, the second level is powered by Node-RED.
Yes.
This is like the real-time traffic control tower. It's an asynchronous platform built for event-driven applications, handling real-time system interactions, processing complex data sets on the fly, and communicating with external messaging mechanisms.
That's a great analogy. The Elira layer defines the route, right? Laying down where the train needs to go. While the Node-RED layer watches the traffic and manages the unpredictable events that inevitably happen along the way.
Right.
Now, to bring those workflows to life, the system exports them as YAML files.
Okay, and for those unfamiliar, a YAML file in this context is essentially a lightweight text document. It acts as a master configuration blueprint, right?
Yeah, exactly. It contains all the container and dependency definitions, and it gets uploaded directly to the user dashboard for execution.
So the system knows exactly what it needs to run because of that YAML blueprint. But a big question remains. How does it know when to run?
Right.
Because we don't want a data scientist having to sit there and push a big red button every time a pipeline needs to execute.
No, manual execution is highly inefficient at this scale.
Right.
While you can trigger, monitor, or stop executions programmatically via the Kubeflow Pipelines API, the time-based scheduling mechanisms inside Node-RED are where the automation really shines.
Okay, how did that work?
Inside Node-RED, there are specialized workflow client nodes. You have the recurring pipeline schedule node, which allows you to dynamically or statically set up a pipeline run. You define a schedule-specific start times, end times, running intervals, and it becomes an automated, recurring execution.
So it's like set it and forget it.
Basically, yeah.
The train leaves the station every morning at 8 a.m., whether you are watching it or not.
Exactly. And paired directly with that is the recurring pipeline event listener node.
Yeah.
This acts as a continuous, silent observer. The moment one of those scheduled executions begins, this node detects it and outputs specific pipeline run identifiers.
Oh, I see.
This ensures the rest of the system, including any external tracking or monitoring tools, knows the process has officially started.
It is a beautifully organized, perfectly rational engine.
It really is.
But here's where it gets really interesting. What happens when human beings actually enter this perfectly organized system?
Yeah.
Because the messiest variable is always us.
Always.
We are not perfectly scheduled nodes. We disagree. We have vastly diverging opinions, especially in those complex medical analyses we talked about at the top of the deep dive.
Right. Human subjectivity introduces a profound challenge in collaborative systems, and the HumAIne sources address this through the feedback consolidation pattern.
Okay, break that down for us.
The core underlying problem here is severe ground truth uncertainty.
Right.
When an AI model is being trained or evaluated, it relies on human expert opinions to understand what is objectively true. So take a complex brain scan, for example.
Okay.
If two leading neurologists look at the exact same image and provide completely different diagnostic judgments, there is immense ambiguity regarding how the AI model should calibrate its understanding.
Yeah. If the teachers are fiercely arguing in the front of the classroom, the student has absolutely no idea what to learn.
That's exactly it.
So how does the framework actually solve a dispute between world-class experts?
Well, it starts by collecting these decentralized opinions asynchronously.
Okay.
Since neurologists aren't sitting in the same room at the same time, looking over the same shoulder, their individual feedback is routed via topic-based messaging exchanges.
Got it. So the feedback is coming in from all over the place on completely different schedules.
Yeah.
One doctor might review the scan on a Tuesday morning, the other on a Thursday night. How does the system even know which opinions belong to the same patient case?
Key-based routing principles solve that alignment issue.
Okay.
The pattern groups incoming expert views using what's called a composite key.
A composite key.
Right. This key is constructed by fusing matching context parameters. So it might combine a specific image ID, a patient ID, and perhaps a timestamp.
Ah, so it creates a unique fingerprint for that specific piece of data.
Exactly a fingerprint.
When Dr. A submits their view, it's tagged with that composite key. When Dr. B submits theirs 2 days later, it gets the exact same tag.
Yes.
So as these asynchronous opinions flow into the Node-RED control tower, the system recognizes, oh, these two completely separate opinions share the exact same fingerprint. They belong together.
You've got it.
And then what happens? I saw in the architecture diagram that it forwards this grouped data to a similarity check function node.
Right. So the similarity check function node mathematically evaluates the consistency of those grouped opinions. If the opinions match. So if both neurologists agree on the diagnosis, the system accepts the consensus.
Makes sense.
The data progresses seamlessly to normal storage, and the AI can utilize it as a highly reliable ground truth for future training.
Let me pause you there, though, because I want to make sure I'm picturing the alternative correctly.
Sure.
What if they don't agree? What if Dr. A says it's a benign shadow and Dr. B says it's an aggressive tumor?
Okay, so the moment a conflict or contradiction is detected between the experts, the pattern intervenes.
Right.
It instantly routes that specific data packet to a dedicated alert output channel.
Oh, wow.
It surfaces the disagreement to a higher medical authority or a joint review board immediately, rather than letting that contradictory data poison the model's training set.
Hold on. I need to push back on this architecture a bit.
Okay, go for it.
Because this sounds incredibly elegant in theory.
Right.
But what's the structural catch here? If we are waiting for human experts to submit their opinions asynchronously, what breaks? I mean, humans take vacations, they get sick, they, forget their login passwords.
Yeah, you've identified the exact vulnerability of this pattern, and the documentation actually highlights it as a severe limitation.
Okay.
The feedback consolidation pattern requires a static configuration. Meaning you must tell the system exactly how many expert opinions it has to collect before it is allowed to run that similarity check.
Oh, I see. So let's say you configure it to wait for 3 experts because it's a highly sensitive case.
Right.
Dr. A and Dr. B submit their reviews. But Dr. C gets pulled into an emergency surgery and doesn't log in for a week.
The system is entirely paralyzed.
Really?
Yeah. If an expected expert fails to respond, it results in an unresolved, blocked transaction.
A blocked transaction?
Yes. The AI pipeline halts indefinitely at that specific validation point because it literally cannot proceed without that final piece of the configured puzzle.
Man, it's just standing at the altar waiting for someone who isn't showing up.
Exactly.
And in a medical context, that blocked transaction means the entire diagnostic pipeline for that patient is frozen. That seems incredibly fragile.
It does, but it represents a fundamental trade-off in systems engineering.
How so?
Well, you gain absolute ground truth security by mandating consensus, right?
Yeah.
But you introduce a massive operational bottleneck if a human component drops the ball.
Right. Okay, the danger of waiting on humans is really clear.
Mm-hmm.
But what if the scenario flips? What if the AI itself is the one lacking confidence and the stakes are so high that we absolutely cannot afford to wait for a static batch of opinions to process?
Right. This pivots the conversation to latency and operational risk. In standard operations, feedback is often handled in bulk. The sources describe the feedback aggregator pattern, where asynchronous events are gathered over time until they reach a configured batch size threshold.
Mm-hmm.
Only when that bucket is totally full is the data pushed to storage to trigger retraining or review.
Which introduces massive system delays.
Yeah.
You are basically waiting for the entire bucket to fill up before you do anything with the water.
Exactly. And in real-time industries like automated manufacturing or intensive care health monitoring, delays caused by evaluating inferences in static batches can lead to catastrophic operational mistakes.
Right.
If a predictive model analyzing a factory assembly line detects an anomaly that could, tear the machine apart, or a patient's vitals are behaving in a way the AI doesn't understand, you cannot afford to wait for a batch threshold to be met.
No, definitely not.
Highly uncertain model predictions must bypass the queue and be surfaced to a human authority instantly.
So how do we engineer a system that bypasses that bucket entirely? I mean, how do we build a framework that flags danger in real time without breaking the larger architecture?
The HumAIne framework utilizes the low-confidence expert notification pattern. Sometimes it's called feedback triggering.
Okay.
Instead of waiting for aggregation, the model is served through runtime APIs.
Right.
As the execution script evaluates a real-time prediction, it performs a crucial extra step.
What's that?
It actively calculates its mathematical confidence rating and injects that exact percentage directly into the output file's custom metadata fields.
Oh, wow. So the AI is essentially stamping its own doubt score right onto the file's metadata before it even sends it off.
Exactly. And once that file, complete with its doubt score, is pushed to the object storage system, the architecture uses a brilliant shortcut.
Okay.
The object storage is configured to automatically post an event notification to an active webhook inside a Node-RED workflow recipe.
Oh, that is incredibly smart. By using an active webhook, you are completely bypassing the delays of those static batches. The object storage itself acts like a highly sensitive tripwire.
Yes, a tripwire.
So, a millisecond a new file hits the storage, the webhook instantly pings the Node-RED control tower.
Exactly. The workflow is triggered immediately. The script inside Node-RED extracts the metadata fields and reviews that injected confidence value.
So the control tower looks directly at the doubt score.
Right. And if that confidence score sits lower than a predefined safety threshold, meaning the AI is mathematically highly uncertain about what it's looking at,
Yeah.
the pattern does not hesitate. It immediately publishes an urgent warning message to a messaging exchange topic.
And the designated human expert, like the shift supervisor or the attending physician, is subscribed to that specific topic.
Yes.
So they get a real-time alert on their end. It's basically the system saying, hey, I'm an AI. I just looked at this incoming sensor data. I'm only 40% sure everything is fine, and you need to look at this right this second.
That's exactly what it is. It completely eliminates the latency of batch processing for critical low-confidence events.
Wow.
This pattern is basically foundational for protecting human safety and maintaining operational integrity in high-stakes environments.
Okay, so the webhook tripwire works beautifully for a single AI pipeline. We've solved real-time alerts for an isolated instance. But this whole framework is supposed to scale, right?
Right.
What happens when this isn't just one AI, but a massive decentralized network of them? You mentioned swarm learning earlier.
It did.
How does the orchestrator even know which humans or nodes are awake to receive these alerts?
Well, scaling this up introduces the problem of what we call opportunistic participation.
Okay.
In collaborative systems, especially swarm learning, where multiple independent nodes, maybe different hospitals or different manufacturing plants, are training a shared model together.
Right.
You simply cannot assume that decentralized nodes will remain online 100% of the time.
I mean, yeah, between technical dropouts, network failures, routine maintenance.
Or just a facility deciding they don't want to share compute power today.
Right. Nodes are just going to vanish.
Exactly. So if you are the central orchestrator trying to run a critical swarm training session, how do you verify who is actually present? If the orchestrator tries to include a node that silently went offline 5 minutes ago, the entire training process could stall, time out, or just fail entirely.
You'd need a system-wide roll call, but a roll call that adapts second by second.
Yes. And the swarm learning discovery pattern provides exactly that.
Okay.
It establishes a resilient online discovery framework utilizing a dedicated fan-out messaging exchange and queue architecture.
A fan-out exchange. Let's translate that. Instead of sending a targeted private message to one specific place, it's basically hooking up to a massive system-wide loudspeaker.
That is a perfect way to put it. Any participating system entity, whether an AI node or a human interface, declares its arrival or withdrawal by publishing structured availability status messages to this fan-out exchange.
Oh.
When a node powers up and comes online, it broadcasts to the exchange, "I am active."
Right.
When it's initiating a shutdown sequence, it broadcasts, "I am leaving the network."
But with a system-wide loudspeaker, you are going to generate a massive amount of noise.
Oh, yeah.
I mean, if you have hundreds of nodes dropping in and out, or a node with a glitch sending the same status update over and over, who is actually making sense of the chaos?
That responsibility falls to a specialized listener component embedded within the architecture.
Okay.
This listener continuously captures every single notification from the fan-out exchange. It processes the data payload, and crucially, it filters out duplicates.
So if a node has a network stutter and shouts, "I'm here," 20 times in a row, The listener knows to just count it once,
Exactly.
preventing the system from artificially inflating its resource count.
Right. Once it processes the verified status, the listener updates a central memory data structure. You can think of this structure as a constantly refreshing real-time ledger that maintains an exact, perfect record of which nodes are active at any given millisecond.
So the listener maintains this perfect real-time guest list. But how does the actual training safely begin? The orchestrator still needs to officially kick things off without accidentally inviting offline nodes into the process.
Well, right before initiating a swarm training session, the coordinating orchestrator basically knocks on the system's door and demands an immediate head count.
Okay.
Technically speaking, it executes a synchronous REST-GET call against an exposed endpoint on that central memory structure.
Let's soften that jargon a bit. A synchronous REST-GET call functionally acts like a bouncer, checking the VIP list right at the door.
Right.
It's a demand for an immediate, real-time answer from the system. Give me the list right now before I open these doors.
Exactly. And because it is synchronous, the orchestrator pauses everything to fetch that up-to-date, fully verified list of active collaborators. Because this happens exactly at the moment before the training phase begins, the orchestrator knows with absolute certainty who is available.
Right.
It completely eliminates the risk of trying to collaborate with ghosts in the network.
So what does this all mean for you listening? We've covered a tremendous amount of ground today.
We really have.
But when you step back and look at this HumAIne library of integration patterns, you start to see the matrix underneath the technology. We started with the foundational engine using Kubeflow for secure, strictly isolated MLOs. And that two-layered orchestration where Elira lays the sequential tracks and Node-RED runs the event-driven control tower.
Yeah. And from that secure foundation, we explored how the system actually tackles the messy, unpredictable reality of human behavior.
Right. The feedback consolidation pattern showed us how to gracefully handle human disagreements using composite keys and similarity checks.
Balancing accuracy with the very real danger of blocked transactions if we wait too long.
Exactly. Then we saw how to completely bypass those dangerous delays using active webhooks to deliver real-time, low-confidence alerts to experts when the AI knows it's out of its depth.
Right.
And finally, orchestrating chaotic, decentralized swarms using a fan-out exchange to track opportunistic participation.
Yeah.
Whether you are just catching up on where AI architecture is heading or you are literally prepping to integrate these systems into your own company, these patterns are the shortcut to doing it safely.
They really are. They turn the highly abstract theories of human-AI collaboration into executable, predictable realities. But there is a broader implication here worth considering. As we study these boilerplate patterns, we are looking at systems becoming incredibly adept at managing human uncertainty.
Right.
Mathematically predicting when we drop offline and algorithmically resolving our conflicts.
Wow, yeah.
It raises a fascinating question. As these integration patterns become more seamless and autonomous, at what point does the AI stop merely being our orchestrator and quietly become the ultimate referee of human truth?
Man, a heavy thought to leave you with as we wrap up today's deep dive. Thank you so much for joining us, and we'll catch you next time.